Hello, in this video we are talking about section 7.3, which is on volume by shells. So we are still finding volumes of solids of revolutions like what we did in the previous section, but now we're orienting our way of thinking in a different direction than what we did with the disk and washer method. And the reason why this is beneficial is that some regions are incredibly hard to represent in terms of a particular variable. So the shell method gives us a way to find the volume by writing stuff in the other variables, so opposite from what the disk washer method allows. Whenever the disk washer method requires the x variable, then the shell method requires the y variable and vice versa. So we are working through example 1 here, where R is the region in the first quadrant that's bounded by the graph of this y equaling the square root of x minus 2 and the line y equals 2. We're going to set up, but do not simplify or evaluate the integrals to find the volume of the solid generated when R is revolved about the given lines. First, we need to figure out what it will be for the x-axis. Second, then the line y equals -2. Third, the line y equals 2. And fourth, the y-axis. So for all 4 of these axes of revolutions, it would be helpful to have a sketch of the region, just like what we saw with the disk washer method and also with finding areas. So starting off, we want something in the first quadrant, first of all. So all I'm going to draw here with our coordinate axes is the first quadrant. Then we're going to have the curve y equals the square root of x minus 2. So we know that the square root function basically has that sort of shape. The square root of x would normally have this point being at the origin, but since we are subtracting 2, our domain now is going to be x bigger than or equal to 2, which means that we are shifting the square root function 2 units to the right. So we're going to have our beginning of our square root function there, and then we'll have the normal square root shape of the function. So that is y equaling the square root of x minus 2. We'll label a few particular points as we get more information on our graph. We also have the line y equals 2. So something like this, and this is definitely not going to be drawn to scale, but that's okay. When y is equal to 2, if we wanted to find our intersection point, we would have 2 equaling the square root of x minus 2, 4 equals x minus 2, x equals 6. So in other words, this point is the point 2, 6. So somehow this becomes x equals 6. And that is why the region is not drawn to scale, but that's okay. This isn't even necessary for full credit. It's just something that's helpful as we are setting up our integrals. So we aren't given any more boundaries except for the fact that we only care about the region in the first quadrant. So bounded by this curve, that line, and restricted to the first quadrant means that we are talking about this region here. Okay, and that's what we are rotating. So the first axis of revolution is the x-axis. So let's start there. For number 1, we are going to rotate around the x-axis. Now, talking about using shells, we need to draw a line parallel to our axis of revolution. To help you remember, it rhymes. Shell, parallel. Okay, so draw a line parallel to the axis of revolution. Notice that is opposite from disk washer, where we would draw something perpendicular. So shell parallel, we're going to have this. We need to find, first off, our radius, which is the distance between our indicative shell here and the axis of revolution. And then we also need the shell height. okay? We also need bounds of integration, but we'll get to that in a minute. So volume is going to equal the integral of, first off, let's figure out what variable we need to be integrating with respect to. For the shell method, it's flipped from disk washer. Disk washer is consistent with the axis of revolution. So disk washer would say x-axis means in terms of x, but shell is flipped. So that means that we need to integrate with respect to y. All right, so if we are integrating with respect to y, this means that we're going to integrate from c to d. We're going to have a 2 pi. Then we're going to have a shell radius. And then we're going to have a shell height. And dy. Now our radius is between this shell here, this indicative line, and our x-axis. So we just want some sort of indicative y value here, which means that our shell radius in this case is just y. The shell height is the length of our line segment. So the shell height is the same thing as the distance from the curve y equals the square root of x minus 2 to the y-axis. But we need to write it in terms of y. So we're going to rearrange this and get that x is equal to y squared plus 2, and the y-axis is x equaling 0. So notice we want a distance, a horizontal distance. In terms of y, we're going to need right minus left, so this is going to be y squared plus 2 minus 0, or just y squared plus 2. So the height function, h of y, is going to be y squared plus 2. The radius is just going to be y. Our bounds of integration, same as with the disk washer method, same as with area, we figure out the smallest value and the largest value for the shaded region. So the smallest y value is here, y equals 0. The largest y value is here, y equals 2. So this means c equals 0 and d equals 2. So putting all of that together, then we have that the volume is equal to the integral from 0 to 2 of 2 pi y times y squared plus 2 dy. And that is our final answer for number 1.